Just checking if it's working. Yep. Great. Hello everybody. Today I need to really get going on this module because I want to show it at Super Booth in May. So I've got about 5 weeks. Today I'm just going to work through putting the microcontroller into the design, because as I said before, the processor I was using was the PGA, well, it was a dev board by Pimaroni called the RP2350. So I'm going to be removing that and putting in a straight RP2350. So I'm just going to be working through that. I'll just start deleting. I don't know if KiCad comes with the part already. Probably should check that before I started. Sorry, I'm just... No, they don't have it, so I'll have to make that. That's the first thing I'm going to have to do, actually. Jesus. Okay. This is the document that Raspberry Pi very helpfully make. It's a complete, quite practical design guide on how to design for the chip. It's changed from the RP2040, which was their first released microcontroller chip, which used a linear power supply, but now it uses, obviously for better efficiency, a switching supply. The first thing I'm going to do, well, and then this evening, hopefully if I get enough time, I've just got the Adafruit Metro. I'll show you in quad view. The Adafruit Metro 2350, which has a PS RAM chip on it on that side. This little one there. An SD card reader. Even has USB host. So there's a lot of features that I want to put into the module. So it's quite good for prototyping. I've got a little display I want to get working as well. I might have a go at that tonight. I'm not sure. But anyway, it looks like the first thing I'm actually going to have to do is create a symbol for this. I'm sure it probably exists. Actually, it might be better just to import it from... So if you look... let's go to the browser. On this document, they should have a link to the design. Yeah, to a demo KiCad project. So I could just import the part from there, which what I'll probably do. Just one moment. You can't see me doing this. I'm just going to pull up the files. Yeah, and they have a library. I might just copy the whole... No, but that's the... Sorry, you can't see this. Oh yeah, there's a schematic. I'll copy it. You won't be able to see me do this because it's in my downloads, but I'll copy it into the project file and then I'll open up. I'll show you it within KiCad. Don't want to show my personal files. I've forgotten where I put everything. Where is it? It's called Euroclerk Green Screen. CD. There it is. Paste. Now, I'm not sure if this is the best. Well, I'll show you within. No, I'll open up and go to this view. You'll be able to see it. It's a bit small, sorry, but there's this library I've just imported from the example folder, which is contains it looks like a capacitor. Don't really want that. The inductor, they have a specific inductor that they want you to use. The QFN footprint and some USB-B. I won't be using that. I might just delete that now. Can I delete it here? No, I can't. Eventually I think I'll integrate them into its own library. And then this lib file, which is the schematic symbol, if I open it, no wait, let me import first. It's best to manage footprint libraries, project specific libraries, and this one, oops, select folder, okay, preferences, symbol libraries, project specific print symbol libraries, and that one, I think it's that, .lib. No, that's not right. Legacy. I wonder why they're using a legacy file. It's called keycard. I just go for this. Should be called keycard sim. Oh yeah. I think they probably included legacy. Symbol files are called .keycad sim, not .lib. I don't know what a lib was. I'll delete that. There we go. Am I going to end up with a crash? Nope. Manage symbol libraries. No. Now if we look in the symbol library, footprint is there. This saves me a lot of work because I would have had to have looked at the data sheet and made my own footprint. But it's good to use the footprint that they supply because it's probably one that's been tested with JLC. Oh, you can't see this, wait a minute. Here, this is the symbol. I'll get rid of that. And it was called, what was it called? It was called MCU. It might just be at what's it called? Wait, this is, no, this is the footprint. This is called RP. This one. So there's this weird. I've kind of made a footprint like that already. This is inductor, specific inductor they want to use. This is the chip. But I don't need the USB. Leave that. Delete the. I'll leave that. I don't know what that's for. Just a minute. So the first thing I'm going to do, I had all these resistors. I had all these resistors here. Don't need those. This is the PGA chip. Don't need those. And then here's the new library I've imported. 80 pin QFN. Makes more space. Let me get to schematic view. This is everything I want to connect to it. Bring those in later. Okay, now that's good to start on the document. So here's document. It's generally good to just work linear through it. So when we first introduced the 2040, we also released a minimal design example. Oh wait, sorry, pardon me. Accompanying the hardware design guide and an accompanying hardware design guide with the RP2040, which hopefully explained how the RP2040 could be used in a simple circuit board and why the various component choices were made. With the arrival of this new chip series, it's time to revisit the RP2040 minimal design and update it to account for new features and also for each package variant. The RP2350A with QFN 60 and RP23B with QFN 80. We're using the B, which is the QFN 80. Again, these designs are in KiCad 7 format and available from here. So that explains why they have the legacy library. We're using KiCad 9. The original minimal board was an attempt to provide simple reference design using bare minimum of external components required to run the 2040 and still have all the I/O exposed and accessible. This was essentially comprised of a power source, a 5 volt to 3.3 volt linear regulator, a crystal oscillator, flash memory, I/O connections, which is a USB connection and GPIO headers. The new series of minimal boards are largely the same, but with some changes necessary due to the new hardware. In addition to this, and despite going somewhat against the minimal nature of the design, we added a couple of buttons for boot select and run. Boot select lets you put the chip into default bootloader mode, which is hard etched into the chip, and run as like basically a reset chip, together with separate single serial, I don't know what that is, it's a programmable header, single wire debug, I think that's what the acronym is, which would mean a thoroughly less frustrating debug experience this time around. I guess the original design file didn't have those in. Designs that strictly speaking need the buttons, and the signals are available on the headers, and they can be omitted. If you are particularly cost or space conscious, or have masochistic tendencies, difficulty. Okay, the 2040 vs the new chip series, the RP2350X series. The most obvious changes is the packages. Whereas the 2040 was a small 7x7mm QFN 56, the 2350X currently has 4 different members. There are two devices which share the same QFN60 package, the RP2350A, which does not contain the internal flash storage, and the 2354A, which does. Now, we're not going to be using these because we want the most amount of I/O as possible, so we're not using the A series, but we're going to use the 2350B. Currently the one with internal flash storage is not available to us. The QFN80 version, which is the 2350B and the 2354B, follows a similar thing. So the only one we really have availability to us right now is the 2350B. I'm not sure what that means for connecting to PS RAM if we had the one with the internal flash storage, which I think is going to actually be soldered on top of the chip. I've forgotten what that's called, the process. But we're just focusing on the 2350B. The QFN60 devices and the original 2040 share a common heritage. They all have 30 GPIO, so yeah, they're quite similar in amount of pinouts. Despite this, the RP2350A is not a drop-in replacement. By contrast, the QFN80 versions have more GPIO than the 2040 originally did, and 8 of these are now ADC, which is really helpful for us. Because of this, we now have two minimal boards, one for 60-pin devices and one for 80-pin. These minimal boards are primarily designed for the parts without flash. However, designs can easily reuse the internal flash devices by simply omitting the onboard flash memory or using it as a secondary flash device. More on this later. There is little difference between the two boards, and the fact that the QFN80 version has more headers for the extra GPIO and the bigger chip, I guess. Aside from the package, the biggest board level difference between the 2350X and the 2040 are the power supplies. This is what I said earlier. The 2350X series has new power pins and a different internal regulator. The 100 milliamp linear regulator of the 2040 has replaced with a 200 milliamp switching regulator, and such requires some very specific circuitry and no little care taken. And as such, it requires some very specific circuitry and no little care taken with the layout. No little care. It means it's strict. It's highly recommended you closely follow the layout and component selections. We've already gone through the pain of having to make several iterations of the design, so hopefully you don't have to. See, this is why you should follow the design guide, basically. The design, it just means that you're guaranteed for it to work first time. Because there are funny things that happen with switching supplies can be a bit more fussy, and the crystal oscillator especially is quite easy to get wrong. The design. The intention of the minimal design examples is to create a pair of simple boards using the 235X. Doesn't really roll off the tongue, does it? The RP2350X series, which should be cheaply and easily manufactured without unnecessary exotic PCB technologies. The minimal boards are therefore two-layer designs using components which should commonly be available and all mounted on top side of the board. We're using JLC PCB assembly, so they have collaborated with Raspberry Pi and they should have those parts in stock, but we'll see. Whilst it would be nice to use large, easily hand-solderable components, the small pitch of the QFN chips mean that using some 0402 passive components is unavoidable. If all the GPIO are to be used, whilst hand-soldering 0402 components isn't too challenging with a decent soldering iron, it's very nearly impossible to solder the QFNs without specialist equipment. Over the next few selections we'll explain what the additional circuitry is for, and hopefully we came to make the choices, and hopefully how we came to make the choices we did. We discussed two separate designs, one for each packet side. As far as it is possible, all of the component references for the two boards are identical. The references, U1, R1, etc. are all equivalent and equally relevant to both boards. The obvious exception is when the component is only on one of the boards. In those cases, the component only exists to be on the QFN80 design, the bigger design. Okay, this is getting into the sort of content of it. So, power supplies of the RP2350X series and the 2040 differ somewhat this time around, though in its simplest configuration it still requires two supplies, 3.3 volts and 1.1, so it's similar requirements but more power, I guess. The 235X series are simultaneously more power hungry, as it's a higher performance yet and more frugal than its predecessor. So the higher performance chip. No. The 20, the whole chip is more power hungry, as it's a higher performance processor. It's an M33 core, I think, which requires more power and more frugal when it comes to a low power state. It has features in it for low power modes, which make it more energy efficient when it's gone to sleep than its predecessor. And so the linear regulator on the 2040 has been upgraded to a switching regulator. This allows us greater power efficiency at higher currents up to 200 milliamps compared to the 100 milliamps previously. That's because linear regulators create heat, which is wasted, so they're more inefficient basically. The linear regulator of the 2040 has two pins. Is this showing the schematic showing the schematic section showing the internal regulator circuit of what? The 2040? Well, no, this is the 2350 because it's got an inductor. The linear regulator of the 2040 has two pins, a 3.3 volt and a 1.1 volt output. So the DVD supply, the DVDD on the chip, the power supply, this time the regulator of the 2350 has a series of 5 pins because it has a switching. Yeah, so you need a. There's no diode though, so the diode must be internal. All switching supplies, buck or boost ones, mainstream switching supplies, have an input, a voltage input, a feedback, LX, what's that again? Ground. And you say all switching supplies need an inductor, a switching element, and a diode. Obviously here, well not obviously, but the switching element and the diode is internal, I'm guessing. Because it's going back into the chip. It's not going onto some circuitry afterwards. So it's quite easy to implement a switch and a diode in silicon, but it's quite hard to create an inductor because it's quite large. Capacitors and inductors tend to be external, discrete components still. While this seems a bit backward step in terms of usability, it's difficult making switching supplies. The switching regulator has the advantage of being more power efficient at higher load currents. The good thing about this though is because they can tell us what components to use and what exact parts to use. It's easy to use if you find it intimidating to design I guess it's a buck converter. As the name suggests, the regulator rapidly switches on and off the internal transistor connecting to the 3.3 input voltage Vreg Vn to the Vreg LX pin with the help of inductor L1 and the output capacitor C7. C7 is the filtering. It can help produce a DC output voltage which has been stepped down from the input, a buck converter. The VREG feedback pin monitors the output voltage and adjusts some on and off ratio for the switching cycle to ensure that the required voltage is maintained. As large currents are switched from VREG VIN to VREG LX, a large capacitor C6 close to the input is required so that it doesn't upset the 3V supply too much. That's because if you're dumping huge amounts of current into the VIN, you can create a lot of noise on the 3.3V supply. So C6 is there to keep the input voltage stable coming in. The feedback is normally a voltage divider if you had it externally, but I'm guessing because this is a fixed voltage, there's only 1.1 volt out, then the voltage divider is inside. It's either a voltage divider, but it's probably a voltage reference inside. No, it'll be a voltage divider because it has to read where the voltage at 1.1 volts is. I'm pointing at the screen, but you can't even see. I'll move the mouse. It has to read the voltage here. Feedback has to read the output voltage and adjust the switching on the LX so that it keeps the voltage stable. C7 smooths it out and keeps it from not moving too quickly. Speaking of these large switching currents, the regulator also comes with its own ground return connection, P ground. Similarly with VREG in and VREG LX, the layout of this connection is critical. And whilst VREG P ground must connect to the main ground, it must be done in such a way that all the large switching currents return directly to P ground pin without disturbing rest of the ground too much. The last pin of V is VREG AVDD. This one. So it's analog power. That's separate, which supplies the analog circuitry within the regulator. Oh yes, yeah. So internally there's it's not like a DAC, it's not like an ADC, but it's like a voltage reference, and it's sensitive to noise. So the first thing we need to do is just copy this, I'm guessing. Input spot, yeah. First thing we need to do is get this implemented then. So let's go to this view. Really need a new mouse. Might be better. Go to this view, I'll zoom in. So I need to implement, I need 3.3 volts. And we're going to the VREG section. Here it is. Nice. I could have probably just copied this from... Maybe I will do that. Great thing about KiCad since KiCad 7, maybe? Is that you can open... Oh god. This project. You can open another project. Go to schematic view. No, that doesn't work. Go back to quad view. You can just copy a section. Saves a load of time. Whilst I'm at it. Oh, you know what? I should just copy the lot. Jesus. Apart from the... I'll copy the lot. Yeah, since KiCad 7 you can actually use the clipboard. So look, the entire circuit is now here. So all I want to do for now, I might just copy this section, 'cause this is the bit we're working on. We'll just move it, sorry. Oof, there's not enough space, wait. Here we go. Let's move this stuff out of the way. So here, I think we'll be going through this. The layout of, well, this is about the layout. Doesn't really mention. Basically, this is a RC filter on the. Can you see my mouse? No, you can't. The you can probably see my massive here. This is an RC filter for the analog circuitry that drives the switching supply. You can work out. You can work out what it's like an easy way to work out what its cutoff would be. Well, there's an equation. We don't need to do that now though. But from the sounds of it, they just want you to use this circuitry as it is. They want you to lay it out. They're telling you to lay it out like this, basically. Yeah, maybe we should, if I update this. Boop. Oh, of course. I don't want this stuff to appear. Don't need this stuff. Delete extra footprints. What? Oh, I haven't saved this. Save. Relink. Delete footprints with no symbols. Might have just deleted. No, I haven't. So we want to work with. Oh, you know what though? And it saves so much time just to. I'll still go through the document, but it just takes just a lot easier just to do this. Oh, bloody hell. Keycard. Right. Now I want some of this, but I don't want all of it. I want this. Okay. Nope, wrong. There we go. This is the core that I want from it. So we've got this switching supply here. This is the power input and all the filtering for it. The USB goes in there, and then these are just all the GPIOs. Some mounting holes, we don't want that. It's the debug header, yes we do want that. And this is a filter for something. Decoupling capacitor for something. A do need to learn a lot of new keycads. Apparently there's a difference now if you go that way. Can't work it out. This is the core that we need. Need to move everything aside a bit. I've already got these debug headers here. Oops, I'm walking off of something. Come on. Oh no, they're not debug headers, they're encoders. Stomach QC. Yeah. Power input. I'll just stick it up there. I kind of want it here. Just need this stuff to go. Oh no, I've done that. There we go. Delete this stuff. Just doing some housekeeping. So we want that bit, and we could probably, because the layout is so specific, could just go to the ATQFN example. And we want this layout here, basically. Just copy that. It doesn't copy the traces though. Oh yeah. No, that might not work. If I updated that, what would it do? No, it just deletes them. We'll just have to look at it, do it properly. Might just do a little bit of layout now. Organisation. This was stuff that I was working on. Bring this stuff back in. We need the RAM. Oh, it's got the PS RAM, cool. And the crystal. The crystal oscillator. I might just attach that. I prefer these to be separate. Bit of a mess this. But this net means this is connected to this. Where's the other switch? Run. Actually, I'm going to do something different. Interesting, you've got a resistor on run. Need to find out what that's about. Just delete that. Because I'd quite like the crystal to just be connected. Just a layout aesthetic. No. Do it like that. Crystals are a notoriously fussy thing to set up. If you get any of these components too wrong, then you can have various batches if they're not working. And we need the primary flash. This is where the programs are stored, because the 2350 doesn't have a then this is secondary flash, the PS RAM. And what's this? Power. We've got our own power, we don't need that. And the debug header. I think we've got a debug header already. Maybe not. I'll put it in. Okay. I think it's good to work on the layout whilst we're doing that. Ideally I would copy, let's upgrade it to the stuff we removed. Ideally we'd just copy it across, because what's the point in copying something by image when you could just copy it across, but it's quite hard to do that in KiCad. So the layout of the regulator on the minimal boards closely mirrors that of the Raspberry Pi Pico 2. A great deal of work has gone into the design of this circuit, with many iterations of the PCB required in order to make it as good as we possibly can. You could place these components in a variety of different ways and still get the regulator to work, i.e. produce an output voltage roughly at the right level, well, enough to execute code, but we found that our regulator needs to be treated exactly in the right way to keep it producing the correct output voltage under a range of voltage load conditions. Whilst performing our experiments on this, we were somewhat disappointed to be reminded that the inconvenient world of physics cannot always be ignored. We, as engineers, largely tried to do exactly this: simplify components, ignoring insignificant physical properties, and instead focusing on property that we're interested in. For example, a simple resistor does not just have resistance, but also inductance. In our case, we rediscovered that inductors have magnetic fields associated with them, and importantly radiate in a direction depending on which way the coil is wound, and the direction of the flow of current. We are also reminded that a fully shielded inductor doesn't mean what you think it might. The magnetic field is attenuated to a large extent, but sometimes does still escape. We found that the regulator performance could be massively improved if the inductor is the right way round. It turns out that the magnetic field emitting from the wrong way round inductor interferes with the regulator output capacitor C7. Oh man, where's C7? Right. Which in turn upsets the control circuitry within the RP2350. With the inductor in the proper orientation and the precise layout and component selections used, then the problem goes away. So it's a bit of a fussy regulator apparently. There will undoubtedly be other layouts, components, which could work with an inductor in any orientation, but they will most likely use a lot more PCB space in order to do so. We have also provided this recommended layout to save people many engineering hours, as we have spent them developing and refining this compact, well-behaved solution. More to the point, we are going as far as saying that if you choose not to use our example, then you will do so at your own risk, much like we already do with the RP2040 and the crystal circuit, where we insist, well, we strongly suggest you use a particular part. We will do so again in the crystal selection of the document. The directionality of the small inductors is pretty much universally ignored. With the orientation of the coil winding is impossible to deduce from a datasheet, and also randomly distributed along a reel of components. Oh, what? Larger inductor case size can often be found to have polarity markings on them. However, we could not find suitable ones in the 0806 case size we have chosen. To this end, we have worked with Abracon to produce a 3.3 microhenry part, which has a dot on it to indicate the polarity. Oh my gosh. I can't believe down a tape they go different directions, and importantly, come on a reel with them all aligned the same way. The AOTA blah 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 are all, or will very shortly, be made available to the general public from distributors. As mentioned earlier, the VREG AVDD supply is sensitive to noise, and therefore we need to be filtered. We have found that the VREG AVDD only draws about 200 microamps. An RC filter of 33 ohms and 47 microfarads is adequate. So to recap, the components used will be C6, C7, C9 in 0402, very specific inductor L1 and a resistor. The RP2350 datasheet has more detailed discussion on the regulator layout recommendations. I'm not going to do that. I'll just copy this then. Wow, that sounds hard. So, we need inductor L3 with a mark showing its orientation, and it needs to go, it needs to go here, and then we need C7. Oh no, they've changed. In my schematic they've changed, so I had to work out which one C7 is. C7 is the one next to the inductor. So in my schematic, for some reason it's called C69, and it needs to go. Does it use the default? No, it's using the 0402 from the. Oh man. I have to hide the reference designators because they're massive. So C7 goes there. And have these FFab layer. Nope, I'm not going to use the FFab layer. With ground facing that way, we need C6, which is this one. Which our case is called C68. This is hard. So we have 1 volt 1 and 3 volt 3 facing left. The ground's on the right. Okay. And then our inductor needs to be positioned a bit like that. And then are those ground pores? Jesus. Oh, are we above the right spot as well? Need our ground to be above ground, and we got 3.3 volts there, and I'll just put traces in for now. Oh, that's too big. 0. Oh god, what's the minimum? I can't remember. We'll be doing 4 layer boards. Traces. Minimum track width for multi-layer boards 0.09, but I'll do 0.01. Oops. Wait, no, 0.1. Should probably set up some design rules as well. No, 0.1 is too big. Interesting. It's probably my design rules. Minimum clearance is 0. No. Not 9. Oh, why am I on FL? I'll be on the top there. Oh, 3.54 mils. It doesn't need to be that small. I thought it wasn't working, but it's because it hadn't changed. There we go. And the ground. Oh, I need to go back to this document. Goes to that ground. And this comes down here. Hope you're enjoying your lunch. Oops. That's 0.2. Might just look at the other design. Yeah, these are just... Why? Let's dim it. Right, how do I select? Yeah, these are just ground pores. Why are they locked? Why can't I select them? Selection fit to all items. Oh yeah. Not footprints. There we go. I might just copy this. There's no point in coming up with something new if this is a proven design. Okay. I've got to work out where I was. I think this needs to be on the centre of the pad. Yeah. So hopefully this will just work. It seems really close. Yeah. This courtyard here is touching this one. Seems right. Oh, stop. I'll just lock this. That's good. You see these wires look different because KiCad now renders them differently. Right, so there's this. Okay, now to the input supply. The input power connection for this design is via the 5-volt bus pin of a micro USB connector. We're not going to use that. We're not using USB power, we're using Eurorack power. We will have a USB connection, but it won't be supplying power, just data. This is a common method of powering electronic devices and makes sense here. As the RP2350 has USB functionality, we will be wiring to the data pins of this connector. As we need only 3.3 volts for this design, the 1.1 volt supplies come from the internal regulator. We will need to lower the incoming 5 volt USB supply, in this case using another external voltage regulator. In this case, a linear regulator, aka an LDO, having previously extolled the virtues of a efficient switching regulator, it would also be wise to choose one here, but we opted for simplicity. Well, actually, I'm going to pass over this bit because we are using a switching supply which we designed in the last video, which is here. Basically copied from the Adafruit Metro. Because in our case we're coming not from 5 volts, we're coming from 12 volts to... oh no, we're coming from 12 volts to 5 volts. Oh, and then we're going to have 5 volts to 3 volts with a linear regulator, but I'm using these low noise regulators, which I'm going to keep. It's not necessary for the chip, but it's good to repeat the same parts because I'm using it elsewhere. But let's just read through this to see what it says. As we need only 3 for design. Oh, I read that already. Firstly, using the LDO is always easier. There's no calculations required to figure out the inductor you should use or how big the output capacitor should be, and the layout is usually much more straightforward too. It's less sensitive to layouts design. Secondly, saving every last drop of power isn't the aim here. If it was, we'd seriously consider using a switching regulator, which I have, because we're going from 12 volts, so if we used a linear regulator we'd have to burn a lot of energy, because with a linear regulator the amount of power you use is the voltage drop times the amount of current you're using. So if we're going from 12 to 5, that's 7 volt drop times however much current we need. So say if we use like 100 milliamps, that's going to be quite a waste of energy. So I've opted to use Adafruit's method of a switching buck controller. Then afterwards, because we're going from 5 volts to 3.3 volts, the voltage drop is much lower, so it's fine to use linear regulators. There wouldn't be much power efficiency saving. I'm not sure if this is suitable, so then after we've gone through this design document I'll probably think about that. They're using the 1117, which is a common linear regulator, has a fixed output of 3.3 volts and can provide up to 1 amp of current, which is plenty for most designs. A look at the datasheet for the NPCP 1117 tells us that this device requires 10 microfarad capacitor on the input and the output. We'll cover that later. Another aspect of the power supply design is the decoupling capacitors required for the RP2350. These provide two basic functions. Firstly, they filter the output of the supply noise, and secondly, they provide a local supply of charge that circuits inside the RP2350 can use at short notice. This prevents the voltage level in the immediate vicinity from dropping too much when the current demand increases. Because of this, it is important to place decoupling capacitors close to the power pins. Ordinarily, we would recommend the use of 100 nanofarad capacitor per power pin. However, we deviate from this rule in a couple of instances. First, in order to have enough space for all of the chip pins to be able to be routed out away from the device, we have to compromise with the amount of decoupling capacitors we can use. In this design, pins 53 and 54 of the 2350A and 68 and 69 of the B share a single capacitor, as there is not a lot of room on this side of the device. This lack of space could be somewhat overcome if we used a more expensive, complicated technology such as smaller components or 4-layer PCBs with components on the top and the bottom side. We are actually using 4-layer but I'm not going to be putting them on both sides. So this is a design trade-off. We have decreased the complexity and cost at the expense of having less decoupling capacitance, and capacitors which are slightly further away from the chip than is optimal. This increases inductance. The trace is like an inductor. This could have the effect of limiting the maximum speed the design could operate at, as the voltage supply could get noisy and drop below the minimum allowed voltage, but for most applications this trade-off should be acceptable. The other deviation from the 100 nanofarad rule is so that we can further improve the voltage regulator performance. We recommend using a larger 4.7 microfarad capacitor for C10, which is placed on the other side of the chip away from the regulator. Okay. Did we get all those capacitors? We can see by zooming out and then selecting them all here. Yeah. Oh, we haven't got the these put in. Go one up. Yeah, we've missed out the C9 and R5. Let's put those in. In this case it's called R6, which should go here. And C71, which goes here. Means to sort of route them like this. We'll work out how to get that 3 volt in later. I might just make these some graphics. I might just make these designated smaller. Filter items by layer, silk screen. Oh no, I've forgotten the numbers. What are they now? 1mm, so we'll make them maximum. Oh, 1mm. You can make them smaller than that. I'll do 0.8. Not 0.8. PCB text items. No, they're reference designators. Okay, slightly smaller. I'll get these decoupling capacitors in, and then I think I'll have to stop until the next episode. Exciting episode. So now if we go back, these are all the decoupling capacitors probably. No, apparently it's these as well. Don't want those. Or those. can move. Oh, I can't. Oh, I've got the resistors too. Just want these. So there basically just has to be one on each power pin. I should really just do it like the schematic, but it's easier just to, every time there is a 3.3 volt power pin, it just needs a resistor. So there. So is this the shared one? 59 and 68 and 69. Oh, it's not those ones. Pin 68 of the 2350B. Oh yeah. Interesting. Oh yeah, because USB comes in there, so we had to be over here somewhere for it. We need one. We need one here. Wonder why. Doesn't seem right there. Pin 58 and 59. 59 and 60. 59. 60. So 60 is, we might actually leave, I might actually disconnect 59, because that's for the ADC. I'll just disconnect that. We're going to connect something special to that. Where I'm deviating from the design. Then we need two more. One, four. And it's 3.3 volt. This pin. Where's the other? Oh, I need one for 1.1 volt pin. And then the next one will be for this 3.3 volt pin. That's for that. This one's for the 1. Oh, that's above it. I should have just copied this. And then need another one for the 3.3 volt at the bottom. Where is it? There. Apparently. I need another one. Wait. 1.1 volt there. Ah, the 4.7U. Which one's that for? C10. Alright, that's perfect. I don't know why they all can't be 4.7 microfarads. And then C15 would be this 3.3 volt one here. The next one is 1.1 volt, the last 1.1 volt. Oh, I put that one in. Oh. What have I done wrong? Ah. That one's not going to be there. I've got the resistors all randomly shuffled up. But they do the same job. Then we need one more 3.3 volt one here. Oh yeah. And then the last one, is it this one? Nope. There's two more. What's that one for? Why have I got a GPIO there and they've got a pin? Weird. Why have I got... Oh, maybe it goes round. This one goes round here, maybe. I can look at this file. Oh, it's completely different. Is it? Oh, that's the A. Yeah, it's the smaller vert chip. So these three go like this, and then the last one is actually coming in here for this one. And this one is for that. I should have just copied it. So it comes in up here. The top is the top part is 3.3 volts. Probably just copy that. Well, I might just do that. No, I'll do. There, that should be. That's where I'm going to stop now. I'm going to have lunch. But then the next one I'll get onto the flash memory, the PS RAM, the oscillator, which is quite important, and then the IOs, but I won't do the headers. And then I'll move on to my customizations, like you saw I disconnected the ADC reference input because we're making that analog synthesizer part. We want to have that. What I might do first, actually, I might copy that idea of having on the top layer a 3-volt pour. I should use it on a wider grid. 3.3 volts. I'll just keep it to the top, because the rest of the circuitry below is going to be analog. Probably want to change the settings to make it just the clearance. What's the clearance? Spacing. Oh. Same. Let's do 0.16. If it's an internal, same net spacing, 0.25, 0.2. Let's do 0.2. No, wait. Okay. So now the 3 volts comes in like that, and we'll copy that same thing that they did, where it's kind of automatically done it anyway. See, the 3 volts comes through. That's enough for now. Thanks for watching. Hope it was classic lunchtime watching.